our speaker is going to be Pierpaola Santarsiero from the University of Warsaw. And she's going to talk about the dimension of the ADP variety.
So, hello everyone. So before I start, let me just give a quick advertisement about this conference happening in Warsaw in October, 26th to 30th of October, on moduli and tensors. You can see a preliminary list of speakers. It's going to be at the Banach Center in Warsaw, Poland. So I think some of you might be interested. So we didn't send the official announcement yet, but since we will send it soon, but I mean, mark your calendar if you're interested. Yeah. So with Charlie Chen, which is over there, in which we are studying dimensions of ADP varieties. Now, these varieties, they come from algebraic complexity theory, so nothing to do with the quantum business. But I still think that there might be some interesting take for the audience in the room. So that's why I decided to present or report about. Let us start. So ADP stands for algebraic branching program. And if we have a homogeneous polynomial f of PDP in n variables, an ADP of f is a direct graph without cycles and with weights that has the following property. So it has one sink and one source. And the vertices are distributed in a disjoint union of D+1 layers, where first layer and last layer they just have cardinality 1. Then any edge only connects vertices from the previous layer with the subsequent layer, and the weight of any edge is just a linear form. So an homogeneous polynomial of degree 1. And here is an example. F has degree 3 in two variables. That's an ADP representation of F. And this is also an ADP representation of the same F. So you see one source, one sink, and then this directed paths connecting source and sink. And yeah, maybe you already understood this from the example, but actually one can compute the polynomial by looking at the ADP, just by considering the sum over all paths from source to sink, and then you just take the products of the weights. So for instance, in this case, we have 4 paths, and this representation of F will be the sum of 4 different things. On top, we have this x1 times x1 times x1, and so that's why we have x1 to the power of 3, and so on. While on the side, on the ADP representation, we only have one path, and this means that F is represented just as x1 plus x2 to the power of 3. Okay? So far so good there. And yeah. And so, as you can see from the example, given an F, there is no unique ADP representation, right? And in some sense, one be interested in understanding what's the cheapest ADP representation or what's the smartest ADP representation, right? So, for instance, in the example, I think we can all agree that the second one is the smartest choice because it represents F just as products of linear forms, right? And this has to do with the width of a polynomial. So if I take F to be homogeneous of degree D, then the width of F is what you see here. So what we do is the following. We take all possible ADP representation of F. For each of them, we look at the cardinality of the maximal, we look at the cardinality of the layers of vertices, and we select the one with maximal cardinality, and then we take the minimum among all possible representations. So for instance, in our running example, here the maximal cardinality of a layer is 4, right? While here the maximal cardinality of a layer is 1. So this means that this is the best choice, and so the ABP of this F is 1. And it's at most 1, and it cannot be better than 1 since F is a non-zero polynomial. Okay, so that's the width of a polynomial. Yeah. In case of the remaining example, the width is so far so good, I hope. Well, now there is a more algebraic reformulation of this ADP notion and also the notion of width, which I honestly like more because you can go quite crazy with these graphs very easily. And so let me show you this alternative definition through this example. So that's a different F, but still homogeneous of degree 3 in 2 variables. So on top you have an ABP representation of the F, and on in the second row you have a matrix representation of this same ABP. So this is going to be given by the product of 3 matrices because F has degree 3. The first one is a row vector, so a matrix with only 1 row. The last one is a column vector. And in the middle, we have a square matrix so that the product is something of size 1 by 1, because we want this representation to actually compute, right? So I didn't make a mistake. And so, for instance, we have a 0 here because there is no edges. There are no edges connecting the set in position to 1. To 1 because there are no edges connecting the second vertex of layer V1 with the first vertex of layer V2, and so on. And in general, if F is homogeneous of degree D, then F, an ABP representation of F, is just writing F as the product of D matrices, or whose entries are linear forms, where the first one is a row matrix, the last one is a column vector, so a column matrix, and in the middle, the matrices of square matrices, so that in the end, you just get something of size 1 by 1. Yes, please. Okay. You have to speak a bit louder, sorry, because I cannot. So you take, what you do is to take, even if there are some layers who have bigger cardinality, then you just take the maximum one. And you put 0.
So if you care about the maximum anyway, yeah, you care about this week. So you just add everything with 0. So.
Okay, thanks for. All right. So yes, that's the notion that we're looking at, and the width now can be seen in this way. So given F, its width is the minimum size that we ask for the matrices. It's minimum R such that F is written as the products of A1 up to AD, where A1 is of size 1 by R, A2 up to AD minus 1, these are of size R by R, and the last one is of size R by R. Okay? Very good. And now, yeah, maybe the first question that you can ask if you like tensors and tensor decomposition in general is, what's the relation with Boring rank, right? With the usual notion of rank for polynomials. I mean, what I just told you, this width notion is not precisely a notion of rank, but it's a number that is attached to a polynomial. Same as the Boring rank. It's a number that is attached to a polynomial. So what's the relation between the two? Here I just wrote down the definition of Boring rank in case you don't recall it. And in general, if our F has Boring rank R, so if F can be written as the sum of R powers of R, as the sum of R bit powers of linear forms, then you can also represent F in this way. So it's going to be less relevant than R. And so Kumar proved in 2019 that if F has rank R and it's given by the xi to the power of t, so the variables, then the width of f is precisely half the rank, or integer part of half the rank. Okay. But now, yeah, what can we do with this notion? Like geometrically, we can do the same as one does with the notion of Boring rank. So we can try to stratify the tensor space with this width notion. We can understand varieties of tens of polynomials with bounded bounded width. And yeah, this is what we are trying to do. In order to be precise, I have to introduce one last piece of notation. There is the IMM polynomial. IMM means iterated matrix multiplication polynomial. This is a polynomial of degree d in capital N many variables, and it's given by the product of these d matrices, where again, the first one is row, the last one is just a column, and in between you have d minus 2 square matrices of size R. And capital N many variables is just where capital N is the number there, and it's just all the positions that you can fill with all these matrices. So it's 2R plus d minus 2 times R squared. Okay, that's the IMM polynomial. And now we are ready to define the ABP variety. So the closure of all the degree D polynomials in N variables that have width at most R. This can be seen as the closure of the image of the following map that sends this A. This is just an homomorphism between capital N and capital CN, C capital M, sorry, and C small n, and A is sent to A of IN. And the image of this
small n should be an R, right?
small,
The small n, like IMM deep n, that n should be an R, I think, because it's a width that you care about.
yes, the n should be an R, yeah. Yes, yeah, here for you some this sign here actually should be an R. Sorry. Thanks. So yeah, essentially what we are saying here is just another word to say that any homogeneous degree polynomial is just a restriction of the IMM. That's what we're saying. And that's what the map is saying. Okay. I hope that this is clear. In any case, this is the variety that we are analyzing. And so our main goal is to compute dimension of these varieties inside the space of homogeneous degree D polynomials in N variables. And so, as I said at the beginning, these varieties come from algebraic complexity theory. Now there are people in the room that are much more expert than me on this. I will tell you what I've learned and what I understand, but I will be very kind of vague. But so, and for the experts, please correct me if I'm saying something wrong. So, you know that there is the P versus NP conjecture, and there is also an algebraic version of this conjecture, which is called the BP versus DNP conjecture, where the V stands for bound. And so what this conjecture is saying is that the permanent is actually much harder to compute rather than the determinant. This is more or less what variance says, because so if we have a polynomial f, then its determinantal complexity is the smallest size of a matrix whose entries are linear forms, and such that the determinant of this matrix gives us the f. That's the determinantal complexity of an f. And this variance conjecture says that the determinantal complexity of the permanent polynomial is super polynomial. So you cannot compute it via big O of n to the power of f of s for any s. And here I substituted the width because actually the width is equivalent to the computing the width is equivalent to computing the determinantal complexity. And so, in a nutshell, we can just say that it's important to understand when the permanent, in which of these varieties the permanent polynomial lies. And so, in a more general sense, it's important to understand dimensions of these varieties. And now, I learned all of this last year at a workshop in algebraic complexity theory. There was this very, very nice talk of Christian Nickelmeyer, in which he explained very in detail all these things. And he also posed as an open problem to compute dimension of these varieties. Both you and I went to the workshop, and so we said, okay, let's try to do something about it. And we started this project. So very briefly, let me tell you some easy cases. So for instance, if D is equal to 2, so if our F is just a symmetric matrix, then you can, it's an easy exercise to compute its width. Then if another very, very easy case is also when N is equal to 2. So if we are considering polynomials in only 2 variables, remember that we are over the complex, so they will factor, and so the width will always be 1. And then another easy case is if R is equal to 1, because we are just looking at F that splits as powers of as products of linear forms. But and this is called the split variety or variety of completely reducible. So these are kind of trivial cases, and this means that the interesting regime is the following. So where D and N are at least 3, and when R is at least 2. So that's the starting point, basically, of the whole stuff. All right, and now I'll tell you about this very first result that we got in the case in which we have many variables. So in the case in which the number of variables, small n, is at least capital N, where remember that capital N is the number of places that you have with the IMN polynomial, that you can fill with the IMN polynomial. And in this case, we proved that that's the dimension of the width variable. And we did this by just very low-level computation. I mean, I don't know how you want to call it. We just computed the rank of the differential of the map at a generic point. Because in this case, since we are looking at the case of many variables, it was quite easy to handle. And so Christian also had this result. We were chatting with him about this, and he asked for a maybe more elegant proof of this same result. Now, we do not have a more elegant proof, but we have a geometric explanation of this number. So this small n times capital N, this is just the dimension of the domain of our map. I wrote it there. Then there is the -1 that just takes into account the fact that we are considering the projective case. And then there are these two numbers, right? Where these two numbers come from. They are in fiber or in the kernel of the differential. And so this first number comes from a group action that leaves the IMN invariant. This is what maybe you want to call it the KH, or I don't know, like a trivial action on the IMN that goes also in the domain and that leaves also the psi invariant. So it's just what you do with this action, you just multiply in the middle of the IMN, you put in the middle invertible matrix times its inverse. So yeah, and so this takes into account this number. And then of course we have this number. And we said, I mean, it was not in this form, it was a much, here it's very nice and you maybe guess what this number comes from, but okay. So we asked ourselves, does this come from another action that fixes the IMM? And the answer is yes. So there is this second action given by this additive group. There is the sum of wedge to CR tensor CR plus CR tensor wedge to CR. And it also leaves the IMM invariant, so it fixes the IMM. And so it only acts on the second and the last but one entry of the space of C capital N. Everything else is fixed. And so on the second level, it sends y2 into y2 plus x1 of block 1. And then on the last but one level, it sends yd minus 1 into yd minus 1 plus x2 of y2, where these x's are skew-symmetric tensors, three-way tensors that are skew-symmetrics in two of the indices. But okay, so we took care of these numbers. At least we understand now where do they come from. And yeah, since my time is up, I will not say much more about the rest. Yeah, at least now we have an expected dimension for these varieties, since we computed the many variable case, and so far we couldn't find the effective cases. And with this I conclude. So thank you for the attention.
So, two questions.
Yeah, so maybe this is the question I just listened to some of the last slide, but talking about this function, this image.
This one? This one?
The image of row 2. So it's saying that like this minus 2 arches 2 is like talking about this action, but it's has cubic sizing of the wedge to use.
Wedge to CR, it's R choose 2 times R. Yes, I remember. Yeah. Thank you. I forgot. So this should be. So the dimension is R choose 2 times R, 2 times R choose 2 times R, right? And then yeah. Thank you.
Questions?